For decades, it has been established that the configuration of spectral lines in a star or galaxy's spectrum indicates its composition and galaxy velocity. Light exhibits analogous behavior to sound in terms of motion. You may have experienced a vehicle with a siren, such as an ambulance, initially approaching and then receding into the distance. The siren emits a higher pitch as it approaches than when it recedes. This phenomenon, known as the Doppler effect, arises from the relative motion between the sound wave source and the listener's ear. As the ambulance approaches, the sound waves are compressed, producing a higher pitch. Conversely, as it recedes, the sound waves are elongated, resulting in a lower pitch. Like sound, light consists of waves. Thus, when a star approaches us, its spectral lines are displaced towards the shorter wavelength, the blue end of the spectrum, analogous to a higher pitch. When a star recedes from us, its spectral lines shift towards the red end of the spectrum. Astronomers can delineate the position and trajectory of stars within the galaxy. In galaxies far beyond the vicinity of the Milky Way, a comparable phenomenon manifests. Edwin Hubble was a pioneer in the study of galaxy spectra. Hubble meticulously observed thousands of galaxies, documenting and analyzing their spectra. His observations disclosed two significant astronomical phenomena. Primarily, nearly all galaxies outside the Milky Way exhibited a redshift in their spectra. This indicated that they were receding or moving away from us. It is crucial not to be misled into believing that the Milky Way occupies the center of the universe simply because all galaxies are moving away from us. Conversely, it affirms that we occupy no unique position in the universe and that each galaxy is moving away from all other galaxies. The reciprocal recession of galaxies is frequently depicted by envisioning sultanas within a fruitcake baking in an oven. As the cake expands, each sultana distances itself from the others, propelled by the enlarging cake. Hubble demonstrated a fundamental law that correlates distance with recession velocity. A significant implication of the mutual recession of galaxies is that the greater the velocity at which a galaxy recedes from you, the more distant it is. Consider three galaxies positioned equidistantly along a linear trajectory, all receding from one another at an identical velocity. Envision our existence in a galaxy situated at one extremity of the continuum. From our viewpoint, the central galaxy will recede from us, just as we will be distancing ourselves from the inhabitants of the central galaxy. However, if we were to assess the recession of the second galaxy, located at twice the distance, it would recede at twice the velocity of the nearer galaxy. This occurs because it moves away from the closer galaxy and retreats from us. The higher the recession velocity of a galaxy, the greater its distance. The recession velocity is proportional to distance, resulting in a nearly constant velocity-to-distance ratio across different galaxies. The Hubble constant has proven notoriously challenging to ascertain accurately. Measuring accurate distances to galaxies is exceedingly challenging. Nevertheless, it is indisputable that the galaxies were situated at a considerable distance. Hubble largely disregarded the theoretical underpinnings of the universe's expansion, whereas Albert Einstein exhibited considerable interest in the concept. General relativity conceptualized space not as an empty chessboard for moving pieces, but as a concrete substance to which all entities are connected. Like galaxies depicted on an expansive rubber sheet, the curvature, flexion, and extension of space affect the positioning and movement of all entities within it. The recession of galaxies did not indicate their movement through space. Rather, it evidenced their transport by the expansion of space itself. This was a significant prediction of general relativity that Einstein initially found difficult to accept. As suggested by his theory, he was deeply apprehensive about the implications of an expanding or contracting universe, prompting him to introduce the renowned cosmological constant to maintain a static universe. Only after Hubble announced his discovery of the galaxy's recession did Einstein recognize that his prediction, excluding the cosmological constant, had been accurate. Certainly, an object must be situated at a considerable distance to experience the effects of the universe's expansion. Consequently, nearby entities such as the stars within our Milky Way galaxy, or even the Andromeda galaxy located 2 million light-years away, remain largely unaffected by the expansion of space. Only over cosmological distances does a high redshift signify a substantial recession velocity, thereby indicating a significant cosmological distance. Before Schmidt examined the spectrum 3C273, the most distant known entities were the proximate galaxies, immense island universes that radiated with the combined luminosity of their billions of stars. Astronomers continue to grapple with the vastness of the universe as elucidated by Hubble's law. To this day, they create maps of the universe by quantifying the redshift of individual galaxies, translating this redshift into distance, and charting the galaxy's spatial positions. We can now revisit Schmidt and his extraordinary discovery. During the 1960s, the measurement of a galaxy's redshift and distance was well established, so Schmidt took considerable time to comprehend the spectrum of the quasar 3C273. After months of contemplation regarding the array of spectral lines, he discerned that the lines he observed were generated by hydrogen, the most elementary and prevalent element in the universe. What perplexed him was their position in the spectrum. They were situated further towards the red end than anything previously observed. The line's significant redshift could be attributed to one factor: substantial velocity receding from the Milky Way, indicating that the object was at a considerable distance. Schmidt measured the redshift at an extraordinary Z0.158 of the rest wavelength, indicating a distance of approximately 2 billion light-years. However, for 3C273 to be detectable at either visible or radio wavelengths from such a distance, it had to possess an unprecedented luminosity, necessitating an energy supply of an unknown magnitude. Quasars undoubtedly represented a novel category of astronomical phenomenon that demanded the attention of astronomers. By the conclusion of 1964, 40 quasars had been identified, some exhibiting redshifts of 200%, suggesting distances of 10 billion light-years, thereby effectively doubling the perceived size of the universe. The suggestion was that this represented merely the surface of a larger issue. This significant astronomical discovery warranted further investigation. If astronomers could not elucidate its nature, they could at least seek additional examples. The Cambridge group has demonstrated proficiency in constructing radio telescopes for radio sky surveys. The Cambridge surveys disclosed increasingly intricate details. Quasars became significant in the investigations, yet their identification required considerable effort. Ultimately, a constraint exists on the extent of the sky traversed by the Moon, thereby restricting that specific identification method. Anthony Hewish, an astronomer who pioneered radio interferometry at Cambridge, conceived a method for detecting new quasars across the sky. However, it necessitated a novel technique employing an innovative radio telescope design. He would require assistance to construct and operate his new design. Among the personnel he employed was a young PhD candidate, Miss S. Jocelyn Bell. Jocelyn Bell rode her bicycle to the observatory as she had frequently done. The interplanetary scintillation array, conceived by Hewish to detect quasars, resembled a vineyard more than a radio telescope, as it gathered radio signals from space and documented them as a sequence of undulating lines on a paper chart. Bell's duties encompassed supplying the recorder with paper and replenishing the inkwells for the recording pens. Her primary responsibility was to analyze the recordings for indications of quasars. During that period, computers were accessible. However, specialists contended that a skilled human could more accurately differentiate between interference and quasar signals, particularly as astronomers became accustomed to the telescope's functionality. Upon examining approximately 100 meters of chart recordings, the 24-year-old PhD candidate attained proficiency in her task. Due to the impracticality of real-time monitoring and analysis of recordings, Bell added and reviewed the extensive accumulation of paper chart recordings. In August 1967, she observed what she would subsequently characterize as scruff on the recording. It resembled neither a natural signal she had encountered nor an artificial one. Enigmatic. Despite its likely insignificance, she annotated it with a question mark and resumed her search through the recordings for quasars. Quasars were a novel and esteemed astronomical phenomenon. These luminous radio beacons were as precise as the stars, yet more remote than the galaxies. What can be so remote yet radiate so brilliantly? What could produce such immense energy that it radiated across the vast universe? The responses to these and numerous other inquiries sustained interest in astronomy. However, the subsequent logical progression was to ascertain the quantity and characteristics of quasars. The star-like appearance of quasars facilitated an innovative approach to discovering additional specimens. Upon observing the nocturnal sky and distinguishing between the star's luminous pointers and the scarce planets, you may have recognized that the planets do not exhibit twinkling. The fundamental reason for this is that, from Earth's vantage point, the planets possess a minor yet discernible diameter. Conversely, although stars are considerably larger than planets, their remoteness causes them to appear as mere points of light. The Earth's atmosphere refracts a beam of light from a point source unpredictably. This minor light scattering results in the star's twinkling appearance in the sky. In the mid-1960s, scientists observed a notable twinkling in the images from point radio sources outside the solar system. The Earth's atmosphere extends only a short distance into space, yet an expansive cloud of charged particles emanating from the sun, known as the solar wind, exists throughout the solar system. Envision this particle flow not as a uniform stream, but as large, irregular masses of diffuse gas erupting throughout the solar system, generating chaotic currents in multiple directions. Starlight remains impervious to the solar wind. However, radio waves exhibit a different behavior. Radio waves undergo diffraction when traversing the solar wind, a distinct form of bending compared to refraction. However, the resultant effect is analogous. It induces twinkling in radio sources, a phenomenon termed interplanetary scintillation. Compact radio sources exhibit greater scintillation than extended ones, and lunar occultation observations have demonstrated that quasars are notably compact radio sources. Anthony Hewish deduced that an effective method to discover additional quasars involved scanning the sky for radio sources. By identifying those that exhibit variability, one could successfully locate more quasars. However, he would require a radio telescope of unparalleled sensitivity and resolution to accomplish this. Hewish understood how to accomplish both objectives. Anthony Hewish participated in radio operations during the war, focusing on technologies to counter aerial radar at the Royal Aircraft Establishment and the Telecommunications Research Establishment, where he initially collaborated with Martin Ryle. Ryle pioneered radio astronomy, was among the first to conduct interferometric radio studies, and was the principal architect of a team at Cambridge. Initially referred to as the Radio Astronomy Group, currently the Cavendish Astrophysics Group, they developed the Cambridge catalogues of radio sources and identified interplanetary scintillation. Hewish's wartime experiences with electronics and antennas, and an inspiring undergraduate course in electromagnetic theory motivated him to pursue radio astronomy. Motivated, Hewish joined Ryle immediately after the war disrupted his undergraduate studies at Cambridge, where he earned his PhD in 1952. Hewish promptly made significant contributions to the nascent field of radio astronomy. He was particularly interested in the behavior of radio waves as they traversed transparent, inhomogeneous media, such as the solar wind. Hewish demonstrated how interplanetary scintillation could be utilized to generate high-resolution maps of the radio sky. Scrutinizing intricate details in the sky necessitates telescopes with larger diameters, which demand increased resources and labor. Hewish addressed the challenge by developing a phased array antenna that emulated the resolution of a radio telescope measuring 1,000 kilometers and performed daily surveys of the entire visible sky. The telescope envisioned by Hewish would utilize an innovative technique for detecting compact radio sources. This technique would detect rapid variations in radio signals, differentiating any sources emitting light at radio wavelengths from the consistent presence of extended sources. This approach would enhance the identification of quasars. He secured funding for the telescope in 1965, which required 2 years for completion. A quintet comprising Jocelyn Bell constructed the array. This radio telescope differs from the contemporary gleaming white dishes. During a summer recess, multiple vacation students installed over 1,000 vertical posts into the ground for Bell and her associates. They installed nearly 200 kilometers of wire and cable between the posts to establish 2048 aerials. The entire array encompassed an area of slightly less than 2 hectares, equivalent to 57 tennis courts. They utilized sheep to control the vegetation surrounding the array, acknowledging that such a complex configuration of impediments would pose significant challenges for any lawnmower. This construction cannot orient itself towards various sections of the sky. However, this is inconsequential as the Earth provides the necessary orientation. Advanced electronic methods enable astronomers to observe directly overhead and down to approximately 30 degrees above the horizon, as the Earth's rotation moves the beam of radio waves captured by the telescope across the sky. The IPS array was several months away from completion when Bell utilized it to search for scintillating sources. She operated the telescope and analyzed and operated the telescope and analyzed the data under Hewish's oversight. While the radio sky traversed above, the telescope examined 4 distinct beams and documented their findings on 4 3-track pen recorders. Hewish's directives were explicit and exact. Examine the recordings and document every noteworthy source. I directed Jocelyn to maintain a rapid reference sky chart documenting the location of each scintillating source upon its appearance in the weekly records, he elucidated. Authentic sources would consistently reappear at the same coordinates, whereas interference would manifest randomly. My method for assessing angular sizes necessitated observations at varying solar elongations, thus requiring repeated measurements. Bell first observed scruff approximately 6 weeks into the program. Later, she observed additional interference in the recording and recognized that she had previously encountered this type of signal. Upon reviewing previous records, she discovered the initial scruff and determined its celestial coordinates at right ascension, 1 hour 19 minutes 19 seconds. While many might have regarded the minuscule scribble as mere interference, Bell perceived it as non-artificial. Moreover, she was acquainted with captivating sources, and this particular one appeared to lack that quality. Furthermore, it appeared near midnight in an area of the sky unperturbed by the solar wind. If it were a quasar, its scintillation would have been apparent. Suspecting it to be a point source, Hewish opted for a more detailed examination. The method employed with a radio telescope involved accelerating the movement of the paper beneath the pens, extending the signal across a broader strip, analogous to creating a photographic enlargement. Hewish directed Bell to install a rapid recorder to facilitate a more thorough examination of the source upon its next occurrence. Hewish recalled that he initially suspected the erratic signal could originate from a flare star, necessitating a more rapid chart speed for closer examination. By October 1967, they had installed the final recorders and receivers and concluded tests based on observations of the prominent source 3C273. The IPS array is now fully operational. Bell frequently visited the observatory to obtain rapid recordings of the object at RA 1919, but he could not do so. After the preliminary observations, the source disappeared. Bell captured solely receiver noise for several weeks. Hewish was apprehensive that the signal had ceased, reproaching Bell for considering it a singular occurrence and asserting that she had overlooked it. In late November 1967, Bell, feeling frustrated, intentionally bypassed her analysis to attend a lecture that appeared more captivating than her customary examination of the recordings.